Hello. All right. Yes, I am Aaron Blohowiak, and I work at Netflix. It's like TV, but online. And I want to first thank all of you for choosing to spend some of your time with me. I want to honor and respect that. Life is short, so I really do appreciate you putting that investment in this. So in this talk, we'll go over just a few things. I'll talk about why Netflix in particular does multi-region high availability and why I think it's something you should perhaps look into. We'll do a quick overview where I will gloss over all of the concepts that we'll talk in for the rest of the talk at once, and then we'll deep dive into each of the three main factors that go into the implications of being in a multi-site high availability architecture. And finally, we will talk about architectural decision points that you have in creating your own multi-site high availability system. So long ago, when Netflix was a small startup, we ran with an island model. So we had a data center or a region in the US and a region in Europe, and everything seemed to be going fine until one day we had a little bit of a whoopsie. And there was an ELB outage in US East. And unfortunately, there was very little that we could do to recover or mitigate from this ELB outage. We had to wait until the provider was able to fix this on our behalf. And we decided that having a huge portion of our users not be able to use the service without anything we could do about it was not a state that we wanted to be in ever again. So we began the process of figuring out how to be more available from a systemic perspective. And it always surprises me how much the appetite to invest in availability rises immediately following an outage. So we had this island model, and the first step in going to having a multi-site high availability architecture was to spin up another region, and that region would only have a proxy. And this let us have it so that if the ELBs in one of the regions were to be down, we could flip DNS to the savior region and then use behind ELB proxies to go back to the region that we had steered traffic away from. This would allow us to be resilient to ELB failures, but still open us up to all of the different types of failures otherwise that could happen in a region. So then we added more and more of the stack to that new savior region, and then enabled active-active database propagation between the two regions in the United States, while EU is still an island. And then we completed the loop where all of the data then was everywhere. So we operated in a three-region model. And at this point, we could completely evacuate any one of the regions, and the other two would save the traffic. So we have the evacuee and the savior regions. That's the verbiage we tend to use. This was good, but it wasn't yet great. We were new to it, and whenever I've been new to something, I haven't been very good at it. It was far better to perform an evacuation and deal with the pain that happened than to let our customers experience pain. But it still wasn't something that we felt confident in. It was still something that we had a lot of anxiety about doing before we would do it. And we had it routinized, but at, say, the quarterly level. That infrequency was caused by this fear and instability. And that infrequency then contributed to further potential instability, because the longer you go without verifying, the more regressions you're going to have and the more surprises you'll find the next time you run it. So this got us caught in this loop. And then we realized that fear is the mind killer, that fear is the little death that brought total obliteration. So we decided to face our fear and bring forward this pain and increase the frequency, even though we knew that it was going to be a kind of thing where we had to have multiple teams watching the metrics and being careful and getting ready to go back to how things were before we initiated the failover. Leaning into that helped us to have a much more confidence in the system, but it still wasn't great because it took a while. It took about 45 minutes for us to completely evacuate a region. Having anything that takes that long when things are potentially on fire increases your cortisol levels, makes everyone much more nervous, and it subjects your customers to excessive pain. Our plan and technique for getting fast is called Project Nimble. It's beyond the scope of this talk, but it is fully documented in the Netflix tech blog. So if you want to know how we went from 45 minutes to 7, it's all there. The important thing, though, is that speed changes everything. Speed made it so that the amount of pain that we were willing to suffer for ourselves was only within about 10 minutes, and the amount of pain for our customers was only 10 minutes worth of loss in a single region. Now, doing that made us much more confident in the system. We really increased the frequency to now start performing failovers every other week. And that led us to minimize the amount of regressions that we had, which then further led to stability, and you get this virtual cycle. Unfortunately, there was still an operational burden. When we would perform a failover, people's pagers would go off because they didn't see any success in the region we evacuated. Now, we know that the best practice is to avoid alerting on the absence of success, but there's not really an enforcement mechanism to ensure that people had set up their alerts that way. So it is a potential distraction. Working with the team that powers the alert service, we were able to make it so that alerts just wouldn't fire in regions that were taking zero traffic. Canaries run in each of our different regions because every region has a slightly different makeup of devices, et cetera. And when we evacuate a region, our canary system wasn't aware of that. So canaries would fail, potentially preventing people from deploying. And if you need to evacuate a region because the region's bad, and then you find out that there's another bug that you need to push a fix out to, but your canaries are all failing because they need to succeed in the region you've evacuated, you can potentially be in an unsafe state. And finally, a lot of our alerts are driven on week-over-week metrics. And if we evacuate a region and then repopulate it, we could potentially have drastically different metrics from week to week. So these are all different things that have contributed to the burden that failover has. However, what we realized is that being able to fail over out of a region so quickly meant that this thing was no longer a burden, it was now an advantage. Leaning into failover and regional evacuation meant that we still had to fight the fire, but at least we could do it when the building was empty. We can now evacuate a region faster than we can frequently root cause or find the triggering incident or bad push or code configuration change that made it to production. And in general, what this led us to do is to lean into recovery instead of prevention. It is my deeply held belief that investing in recovery is superior to investing in prevention because prevention techniques tend to mitigate or reduce the amount of errors for error conditions that you can imagine, but recovery techniques can compensate for things you couldn't even imagine before. So for instance, a region going down. The number of reasons and ways in which the complex system can fail within a region are innumerable and unimaginable. But being able to evacuate a region lets you mitigate the vast majority of them. Trying to prevent each failure mode that you can conceive of ahead of time is a lot of work. It's incremental cost for each new thing that you can imagine. And you end up having to pay that cost with each new amount of development that you have. So now I'll do a brief overview of the dynamics at play once you enter the high availability setup. So the main problem that we have is we have global demand, and this demand in many systems varies by hour. This is not an accurate depiction of Netflix demand. We have to serve this global demand, and usually we scale our systems to the peak of demand, right? So that amount of scale required to power peak, if we were running in one region, we'll call 100% capacity. So how many regions should we have? Well, what we want to have is an n+1 architecture, where n will be the number of regions that have to operate, and 1 would be the spare that you can potentially lose. In one region, you don't have a spare, so you can kind of think of it as a 1+0 architecture, or 0+1, where you have one region with 100% of your capacity. With two regions, each region would need to be able to serve your global instantaneous peak demand. So you have 200% of your capacity cost. But with three regions, things start to get a little interesting. What you can kind of figure out here is now any two regions equal 100% of your global peak demand. But if we add the capacity for all three regions, it is 150%, not 200. So it's surprising that it can actually be cheaper to add regions. So let's just take this 2+1 architecture as our example going forward for the overview. So as we saw here, the capacity we want to have as the limit would be 50% of that global instantaneous peak demand. So we'll just add a line to our graphs at 50%. And then to maximize, or rather to minimize the maximal loss of a region failing, we want to evenly load across all of our regions throughout the normal course of events. So if I have 3 regions worth of capability, having 33% of our load in each of the regions in the normal case minimizes the maximal loss of a single region failing. So if we were to unevenly load the regions, on a risk-adjusted basis, we would actually have the same amount of expected streams lost, so streams being like people being able to play, but we would potentially open ourselves up to having bigger outages than required. Does that all make sense? All right. So what we want to do then from an availability perspective in the normal case is to have 1 over the total number of regions. If we do in fact have a steering policy that sends more than proportional load to one of the regions, such as the purple line here, we've introduced now this notion of excess risk, where if that region were to fail, a larger population than would be minimal or required would potentially experience the outage. Additionally, if our steering policy made it so that one of our regions exceeded 50% of our global instantaneous peak demand, we now have risen above our cost minima and are now experiencing cost suboptimalities. And because we reserve our instances or we prepay for our capacity, we're going to experience that overage 24 hours a day in terms of cost. So here's an example for one of the potential steering policies. It gets a bit more complicated than our toy example. And this is just to show you that, yes, we do in fact use these techniques where we shade the graphs and can visualize potential cost overages. This black line would be 1/3 of global instantaneous peak demand, and the different lines represent the different regions and their demand throughout the normal case. All right, so now we'll move on to algebraic models. Within availability, we have to think about how we can minimize the impact of production changes. It's the name of the game. If you make global changes, regional isolation is just spending a lot of money for not a whole lot of benefit. So use the isolation that you have to minimize the blast radius of all of the events. Remember, we still have to do the firefighting, but at least we can do it when the building's evacuated. So how many regions should we have? In our example, we use 3, but how far does it go and keep on adding regions? Well, you can see that as we add regions, we can continue to shrink and shrink the failure domain, or the size of our population which is subject to potential fault, assuming that only one region goes down at a time. What we also notice, though, is we have diminishing returns as we add regions. That's because we're increasing the denominator. Math people, is that right? All right. And then how should we balance traffic? So I talked about wanting to evenly load the regions in the normal case, but frequently for latency reasons, you may not want to have them be perfectly evenly loaded. So we want to be able to quantify that shaded area of the graph. So this is a fancy way of expressing, like, just capture the area of the shaded portion. So for each region, for each hour in the day, take the max of 0 and the amount that this region is over proportional global traffic. So here we can see that for each hour, we take the little bit, a bigger, 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 and bigger portion, and that would come up with our total excess availability risk score. Now, we didn't just want to use the theory behind it, so what we did was we took all of our historical incidents for the past 4 years and replayed them against different steering policies and different amounts of regions to be able to come up with the new projected stream savings for each different steering policy. If you have fine-grained data and good tagging to know if adding a region would have reduced the blast radius of an outage, you can go ahead and do this technique. Latency is the other big reason to potentially pursue multiple regions. Having your compute closer to users can reduce latency. When you think about which latency you want to optimize for, though, we have to think about, do you want to optimize for latency in the normal case, which should be the overwhelming majority of hours, or and then also perhaps during the failover case. So if the failover case is infrequent, then latency may or may not matter, depending on the kind of application that you run. So to think about that distribution of traffic across all the regions now, we have the availability threshold, that's 1 over the total number of regions. That cost threshold, which is 1 over n, which is number of regions minus 1, or the required amount of regions that you have. And for latency, it's really application specific and dependent. You're going to want to do that kind of research to figure out what your population can tolerate when. Another thing about traffic distribution is that this sort of peaks and valleys is very common across many different applications. And the Pacific Ocean is quite large and not very inhabited. So you're going to frequently have this nice dip where you can perform all kinds of operations and things. So how do we quantify the difference in latency between different steering policies? We like to think of latency not as a single number, but as a distribution. So this is a cumulative distribution function, or basically, as we have each observation, we're going to increase the percentile of observations, if you will, and then the latency that we have at that percentile. And this would be for a single steering policy. And then if we have another steering policy, it has a different cumulative distribution function. So now the tricky part comes into how do you compare these? We could use that area trick that we used before for measuring excess availability, but we don't care about all of the different parts of our distribution equally. Frequently care more about what the worst case scenarios or the bad case scenarios are when we operate our services. So what we want to do is to sample the differences with an increased frequency higher up in the distribution, and then we can sum the difference of all of these samples. Now, addition and subtraction is commutative, so you can either take the sum of the differences or the difference of the sums. It doesn't matter. So here's the fancy way to describe that. We did it. We thought we were super duper clever coming up with this, but in reality, it's basically the same as taking the 95th percentile. So one of the things when you go to your boss and you tell her, hey, we should totally look at multi-region high availability, one of the questions you'll frequently get back is, but what about the cost? So with this 2+1 architecture, we got in theory to 150% of our global instantaneous peak demand supporting cost. And as we were to add more and more regions, we would shrink that failover overhead, right? The amount of throughput excess capacity that we would have to have. So at one region, we have no increased availability, but only 100% of cost. With two regions, either one needs to support 100% of traffic. With three, any two need to equal 100%. So you get 3 times 50 equals 150. With four, any three need to equal 100%, et cetera, et cetera. So you get this nice sublinearity. If your application's cost were exclusively throughput. So in an n+1 architecture, the overhead's 1 over n. And the cost is 100% plus 1 over n. Again, that's only if your costs were purely throughput-based. So if we have 100% of your global instantaneous peak demand costs in one region, some portion of that is going to be due to your data. When I say database cost, it's not necessarily just your database, but the cost to have your machine images, the basic infrastructure, your minimal footprint per region, regardless of how much throughput you have. If we have all data everywhere, then this would be your full data cost in addition to these other fixed costs per region. So in that 2+1 scenario that we were discussing with all data everywhere, we're now definitely going to exceed 150% of our global peak instantaneous demand cost. So we have this database portion, which is the orange portion, and the throughput-based portion, which is that blue portion. And the notion that all data is everywhere, that's the region replication factor of all. So like all your data is everywhere. In this scenario, we can come up with a simple equation for how we calculate the cost. It's going to be 100% minus the database portion, so that's your throughput portion, times 1 plus 1 over n. That gets you your total throughput cost for the number of regions that you have. And then your data cost is just your total cost times the number of regions. So then how does that actually play out? Well, this blue line is if your database portion is 0, so that's what we just saw a few slides ago. That's the theoretical minimum. And then as the database portion increases as a function of that 100%, you find that the knee in the curve moves from the higher regions to the number of lower regions. So for instance, this red line is if 5% of your costs were your database, orange is 10, green is 20, purple's 30. So the larger that your database footprint is, the more expensive it becomes to run in multiple regions. The reason I chose 2+1 as the example before is not only that that's how we run, it's also this very common knee in the curve for these things. For some applications where your database portion is lower, 4 may be the magic number for you with all data everywhere. However, if we can make our system work in such a way that each person's data or each user's data is only in 2 places, then our cost curve changes. Now we no longer have any portion that grows as a function of the number of regions. We have the pure sublinearity of reducing our failover overhead with a fixed database cost of 2 times our one region cost. So that's pretty interesting in that dynamic of going from all data everywhere to only having 2 copies of the data. So as a cost summary, you have 50% of your throughput overhead plus your triple database cost when you have 3 region all data everywhere, and you have 25% throughput overhead plus a double database cost for 5 regions with data in only 2 places, and a heck of a lot of complexity. So now we'll dig in a bit about the architecture of how to make all this stuff work. In order for regional isolation to work, you can't make cross-region requests. Seems simple, but you'd be surprised that even very sophisticated engineers who believe in multi-region high availability architecture still say, oh, but this one system should be able to call that other region. Just, it's a very low throughput, it doesn't really matter. Well, that's all fine and dandy until something goes wrong and now you're self-DDoSing. Or you've saturated the link between the 2 regions and now your database replication's getting slow and all kinds of things are going wrong. So no cross-region requests. Your services should all be stateless or use asynchronous replication. Because again, that's all about isolation, being able to shield yourself from bad actors, even if that bad actor is you. One interesting thing that we discovered was that not only do we want to replicate our databases, our persistence tier, but we also needed to replicate our caches. Many of us here use caches to increase the throughput of our systems, but if you were to evacuate a region, then you have a whole bunch of now cold cache calls. So you could scale up your persistence store to handle the throughput, or you could replicate your caches. Again, change one region at a time. I cannot emphasize that enough. So this whole all data everywhere, or all data in 2 places thing is basically sharding or not. Sharding your data and sharding your users. And that's the question that's going to drive many architectural decisions. And it may very well make sense to start with all data everywhere and then migrate to data being sharded and only in 2 places. Steering. Being able to send any user to any region is hugely powerful. It means our client applications don't have to have any awareness of multi-region. It means our ability to steer can be as simple as using GeoDNS or DNS resolver prefix steering. We don't have to worry, what if somebody shows up in the wrong region? Because there is no such thing. With having user-specific steering, you have to pick, are you going to do it at the application layer? Are you going to have a bunch of proxies sitting in your POPs at your edges that then direct users to the right region? Or are users going to show up at any region and then pay for another cross-region hop? Those are all the kinds of things that you have to think about when you get into data sharding. Rebalancing our traffic with all data everywhere, super simple. Just send people to a new region. If our data was sharded and people could only show up at regions where their data lived, now we have the problem of having to rebalance or rehome data. So if you have a service-oriented architecture with 100 databases, being able to say, oh, all of this user's data needs to now move to this other region, that could be pretty hard. You could potentially group users together and now move shards instead of individual users. That's shifting around your complexity and flexibility in the space. Cost is a great reason to shard, though. As we saw in those graphs, being able to have your data in only 2 regions really lets you take advantage of that sublinearity of adding regions. Finally, the models I presented earlier assume that all of the regions equally participate in failover. So they all basically have to have the same minimal size. But what if you have a bunch of users that live on an island in the middle of the ocean and you want to serve them very well? Well, you probably want to spin up an additional region near them. But you shouldn't have to bear the entire cost of having all of your data there. So that's one potential reason to shard. Sharding may not work for you if you have a real graph between all of your users. With Netflix, we have the nice advantage that you have your account with multiple profiles, but there's very little, if not no data that goes between your account and another account. So some people operate a graph where each of their users are pulling data from all of the other users, and that sort of thing makes it quite tricky to figure out how to shard your data. So how do you actually pull this off? How could you have your data in 2 places while diminishing the failover overhead as you add regions? You might think, oh, well, let's be in 4 regions and have 2 different pairs of one-to-one replication. But then you've actually still just doubled your cost. You've now just split it into 2 buckets. Well, there are 3 different ways that we can think about to achieve this. And the central savior is the easiest one to visualize. Here, any one region could fail, and there's another region that has the same copy of that data. So you could imagine we would segment our users into 4 buckets, each identified by a different color: purple, green, yellow, and red. If red were to fail, well, then all the users could be handled by that center one. We call that like a central savior kind of model. What's really nice about this is now all of your data is in one place. So if you need to run BI or business intelligence kinds of functions and say, hey, query everything, it's now all in one region. You don't have any cross-region communication. The other nice thing about this model is it lets you add that satellite region I was talking about earlier with the cost proportional only to the throughput cost for that satellite. So this database cost is being stolen from the other buckets, so it's not actually an increase. It's just this additional throughput. And the size of your savior only has to equal the size of any of your other regions around the ring, if you will. Another way to achieve region replication factor equals 2 is to operate everything in a ring. So I apologize for how awful this visualization is. If any of you are skilled at visualizing this and can tweet at me or email me a better way to represent this, please, please, please do so. That's my Twitter handle. So what I am attempting to visualize here is 4 regions denoted around the outer side of the ring. Additionally, we have 4 buckets of users, each denoted by a hue. So we have blue here on the left. And we have the dark blue and the light blue to show that there's 2 copies of the blue data. We have green, similar thing, 2 copies of the green data. We have orange, 2 copies, and purple, 2 copies. But the 2 copies are distributed around the ring. And what that means is when any one segment of the ring were to fail, there's now still a region that can serve each of the different colors. So if you were a green user, you can still go to a region. If you were an orange user, you can still go to a region. Now, if these neighbor regions had to absorb all of that load, we would still have a significant failover overhead. But if you notice, the black region, it has data in common with its neighbors. So it could grow just a little bit. And now we can close that ring and serve all of our traffic without any 2 segments needing to grow by a large amount. So what's interesting about this is that you can have only 2 copies of the data evenly distributed around the world, and the world is pretty much a circle if you look at it from any angle, I guess. But again, you have to contend with the Pacific Ocean, so that may throw a wrench in this plan. So for my closing thoughts, I want you to consider the potential of having high availability architecture achieved through multi-regions. It's extraordinarily powerful to say, no matter what you do to one region, we're going to be okay. We still have to fight that fire, but at least we can do it after we evacuate the building. Now, that's not entirely true, because if you write bad data to a database that then is replicated worldwide, whoopsie-doopsie. So, all models are wrong, but some are useful. And it can cost way less than you think. Most people assume that going multi-regions can at least double their costs. It's just not so. When you think about having disaster recovery plans or operating in a pilot light mode, that can be good, but how frequently are you actually spinning that up? How frequently are you validating it? Using multi-region as an availability play not just for disaster recovery, but as an operational skill means you exercise it all the time. It means you have high confidence that it will work. And that helps me sleep at night. Also, we're hiring. And follow me on Twitter. All right, any questions?
If you have questions, I would like you to use the microphone for the benefit of the recording. I'll just pass it around.
Thanks. So all of your analyses initially presuppose a N+1 architecture, which means that if AWS loses 2 regions, or whoever your provider winds up being, loses 2 regions, at that point, everyone has to go outside and play, which is terrible. Was that weighed in when you were debating what this was going to look like in the final analysis, in that multi-region failures are rare enough that that's a black swan you don't have to plan for? Or was that just a trade-off that oops, no one thought about that before.
Right. So to summarize, why n+1 and not n+2 or n plus m? Having more than one region's spare capacity gets even more expensive. And having multiple regions being down for the same reason is quite rare. So then you get in the game, not of everyone should go outside and play, but how many people have to, in which case. So if you have 3 regions, each supporting 50% of capacity, and 2 of your regions go down, you can still save half of your users. So that's pretty powerful. Instead of having 0, it goes to half. Now that's not great.
Premium users.
The comment was about having a quality of service lane for, yeah, exactly. So that's a very interesting point. You have to crunch your numbers, think about the sources of your outages. When we look at the numbers of the causes of incidents, our provider is quite good about doing regional deployments and changes. So it's very infrequent that our provider has multiple region outages for the same cause. Self-induced, we're still learning that lesson of really embracing regional isolation at all levels.
So my question is about, you talked about constantly adding regions, and there's a strong dependency around sort of how the services operate, and you talked about this, about ensuring they're stateless and async, and about additionally the data layer. So how does your team manage forcing that requirement onto the teams? How does it, do you have a middle layer that allows you to, I don't know, test that the services are async or stateless, or do you have a lot of control over the data replication?
So I guess there are 2 different answers. One sounds better and the other is more accurate. So the sounds better answer is we believe in freedom and responsibility and context, not control. So the context is set that we want regional isolation. And then the responsibility goes to everyone to figure out how exactly they're going to achieve that. Now, the team that provides databases as a service has this operate for you without you having to really think about it. Now, if in your queries you say, yes, I want global quorum, well, you done messed up. Now, the more accurate answer is we evacuate regions every 2 weeks. So when someone messes this up, we'll find out. And because we're doing it in a planned way, we'll identify it and abort that failover within the matter of a minute. So routinization, frequency, that's how we get there, without having to have middleware and control. And I think that might be an undecidable problem, depending, or you could do network isolation. We do have network isolation because we use security groups and these kinds of things in our cloud provider. But being able to poke a hole in that is an API call away. So.
So your cost function focused entirely on throughput and data, but aren't there other costs there, like constant factors per region, the overhead, extra overhead of deployment, things like that? Like, are those 2 so dominant that the others didn't matter, or are you just like kind of simplifying a little bit?
So that's a matter of scale in terms of whether or not those fixed costs will be material to your cost function. The database cost is a bad term that's easy to understand. So the actual function has several more terms. So you have your data cost, you have your true fixed cost per region, you have your inter-region communication costs. So if you're going to replicate your writes to multiple regions, you have network costs. That tends to be substantially lower than your data at rest costs or even data throughput costs. You also have not only the overhead of having to have your AMIs in each region, but you have developer overhead, right? When you have 2 regions, you know what's going on with this one or that one. When you go to N regions, it's kind of hard to keep track of it. Another cost, how long do deploys take? If you're doing regional isolation, you have 4 regions, and you want to be able to actually have confidence that you'll see perturbations or disruptions introduced by having a new version roll out. Well, now you could be thinking about deploys taking hours, whereas before they were taking on the order of tens of minutes. That could be a potential downside. Your alerting system should also then become much more aware. Again, the deployment system, we talked about canaries failing. Well, to really figure out how to preserve developer velocity, your deployment system should make it just work. And be able to route around failed out regions, and then only do the deploy once that region's repopulated, et cetera, et cetera. So there are lots of other things that go into play. But whenever I start to analyze a potential decision, I think about the high order bits, and then I drive down from there. Because I want to stop going down a road as quickly as I can, if you will.
Hey, if I understood you right, I think your model kind of depends on the assumption that each user more or less generates the same throughput, right? So how does the model change if a large amount of throughput comes from a very small amount of users?
So I guess it also goes back to how much scale you have. So if you have a small amount of users, but that small amount is in the hundreds or even low thousands, even if you have a much larger total population, if you can distribute that small amount in such a way, then you still will be okay. So again, there are definitely different types of applications which this kind of thinking may not be valid for.
Any more questions? Oh.
Thanks. Did you consider any other alternative beside the n+1?
So alternatives besides n+1. So I think I talked a bit about n+2 and the potential cost dynamics of that. Other alternatives to achieve high availability are really interesting. So one of the very fun things that we considered, but ultimately decided not to go with, is a degraded mode. So our application has the nice property that a non-personalized experience is still a valid experience. Right? If we don't know exactly which episode you left off on, but you could still search and watch anything, that's great. It turns out it requires far less computing power to give non-personalized experiences than personalized ones. So there are ways of achieving cost sublinearity by adding regions, or rather, to support high availability without having to have all the data everywhere. So, yeah. There are other applications where, if you think about all of the causes for regions going down, very few of them actually involve the database going down. So maybe it's okay if you're very cache heavy to have your databases only live in 1 or 2 regions, but have your caches be distributed worldwide. That's how some other sites that operate at similar scale happen to operate. But then you really have to be clever about knowing where your caches are. If you want to read your write, then you have to then redirect your reads after your writes to a different region, et cetera, et cetera. So you just shift your complexity and cost around.
We've got time for at least 2 more questions.
Have you had to rethink this architecture at all in the face of political considerations like GDPR?
Nope. And the reasons why are outside of my area of expertise. So by a quick show of hands, who was surprised by the cost sublinearity? No one was. Oh, that's very interesting. I said by a quick show of hands, who was surprised by the cost sublinearity? All right, by a quick show of hands, who found this talk useful? Well, thank you very much. I really appreciate it. You all have been wonderful. Please feel free to find me, catch me, harass me, tell me your feedback. I really want to learn from all of you. Thank you.